For any machine, the efficiency can be defined as the ratio of the output upon input. Okay, so same is the case here as well. So here also it is output upon input. And what is input? Input is output plus losses. This is also well known fact. Okay, so here also same thing applies. So let's say this is our efficiency. So it is output and this is output upon input. Okay, and this input is equal to output plus losses. Okay, and this can be derived from KVL as well. Okay, for example, uh, you can say that if something is input is given, this input can be voltage or power, and some output is received. So within input and output, what happens? Losses are there. Okay, be it any machine, same is in the case of transformer as well. So these losses are there. So if we are going to apply the KVL, what happens? That input, for example, we have studied that this is EMF, say this is say voltage across the load, and this is say resistance R, then what we can say, V is equal to V plus IR. Okay, so now in case of the transformer, here we are talking of the power loss. Okay, so these losses can be divided in two parts. One is the fixed losses and other is the variable losses. Okay, so what is the difference between the fixed losses and variable losses? As the name suggests, the fixed losses will remain fixed irrespective of the load. Okay, whether it is the transformer is in no load or whether the transformer is in full load, it is not going to affect. Okay, so the fixed losses will remain so same. Fixed losses occur in the core of the transformer. Okay, so the core losses are termed as fixed losses, and in general these core is made up of ferromagnetic material or ferrous material, or you can say iron material, iron or its alloys material. Okay, or so these losses, these fixed losses are also called iron losses. Okay, so we can say these fixed losses is equal to iron losses. Okay, and in the theory part earlier we have discussed what are these iron losses. So these iron losses can be categorized in two parts. One is the hysteresis loss and other is the eddy current losses. Okay, so these losses are fixed irrespective of the current which is flowing to the load, whether it is flowing to the load or not flowing, no load condition or full load condition or half load condition, it is not going to affect them. Why? Because these hysteresis loss and eddy current losses, we have seen the formulas of these losses. It depends upon the flux density, maximum flux density, frequency, thickness of lamination, but it does not have any current component. Okay, so these losses will remain fixed. These are categorized as fixed losses. So there are few other losses also, say windage friction losses due to wind or any friction also. But since first of all the transformer is a very efficient machine, so in laboratory conditions also we can get the efficiency of 95 to 96%. Okay, and under controlled conditions 99% efficiency is easily achieved. So the component, those components, say friction, windage, losses, so these are neglected at the moment. So now what is the copper losses? So variable losses are copper losses. First thing first. Okay, variable loss is equal to copper loss. Okay, now the question arises where the copper loss is. Copper loss is there where copper is, and where the copper is used in conductor. Okay, so whenever there is losses in the conductor, it is termed as copper losses. And how the losses are there in the conductor? Due to the flow of current. Okay, so these are conductor losses, and conductor losses are the function of current. And why does this current flow? Current flow when there is the connection of load. This current, we are talking of the load current. Okay, because distribution transformer is connected in any society or in any living area which you are living, wherever you are living, it is connected by one or many distribution transformers. So your house is termed as a load center for that distribution transformer. So whenever you use the electricity, the current is consumed, that load current is drawn from the distribution transformer, and that is drawn to the conductor, and conductor are made of the copper. So these are copper losses. And why they are called variable losses? Because our current or the load requirement changes every second. So the copper loss is termed as the variable loss, and the losses in the conductors are I square R losses. So these are I square R losses. Okay. So this R is not the load. This is not the resistive load. And since this is I square R losses, this can be I square R or I square X, or in general, we can say I square Z. Okay. But this is not the load. This is the components, undesirable components of resistance and reactance, which are present in the primary side and the secondary side, across which the drop happens. And since the drop is happening and current is flowing, so I square R losses are also there. So now we can talk of the load. So this is our core, this is our secondary side where the load is connected. So let us assume there is no drop. So when there is no drop, this is E2 EMF, and all this voltage E2 will come at V2. Okay. So this can be resistive load, reactive load, capacitive load, whatever it may be. Okay. So if the full load, if the transformer is operating on full load, okay, when it is operating on full load, it means that the full load current will flow. Okay. So when full load current will flow, the losses will be I square Z, where current is full load. Okay. But if say our transformer is operating on half load, so if transformer is operating on a half load, then the current becomes half. But when the current becomes half and we square this I by 2 score, so our copper loss, if this PC is our full load copper loss, then On half load, the copper losses become 1/4. Okay. So ultimately, we can say that if X is the fraction of the current of the full load, if you can say 60% is flowing, then X becomes 0.6. Okay. So if X is the fraction of the current, full load current which is flowing, then the copper loss become X square PC. So output is, first of all, these losses are measured in watts or kilowatts. So the output should also be in similar terms. So Q is the, you can say, the output at full load. So if it is at full load, then say this is our V2, secondary side voltage. This is secondary side, so it can be out to I2. So, but the from the power triangle in the single phase circuits and the three phase circuits, what we have studied, that if we have to take the real power, it is to be multiplied by cos phi. Okay, which is the power factor. Okay, so if the power factor is given, it's good enough. It is not given, take as unity. Okay, so now let us assume that this is unity. Okay, so this is the I2 is what, this is the load current. So if the full load current is flowing, it's good enough, but if the fractional load current is flowing, then this is xi2. So if this v2 I2 is q, then it becomes xq. Okay, is this clear to you? When we will be doing the numericals of these types, it will be more clear. Okay, so at the moment it is clear. Okay, okay. So now we have to just apply this formula. So now applying the formula, what we get, output upon input. So output is xq, then input is output plus losses. So it is xq plus pi, which is the fixed losses or the iron losses, and x square pc is the copper losses or variable losses. Okay. So now another question arises that when will be having maximum efficiency? How can we draw the maximum efficiency from the transformer? Okay, so we will be derivating this efficiency formula, and derivation is done with respect to variable quantity, and the variable quantity here is the current. Okay, or you can say x factor. So the x is the fraction which is variable. Okay, so d neta x upon dx is equal to 0. We will differentiate, substitute it to 0, then we will get the critical values, and while solving this we will get pi is equal to x square pc. So what does that mean? It means that the maximum efficiency is obtained when fixed losses or constant losses are equal to variable losses.